Hello students, welcome to the class. In the last class, we started with mechanical properties of solids and fluids. In that, we discussed the mechanical properties of solids already. So in fluids, we have discussed what is viscosity, we discussed force, surface tension, the factors affecting surface tension, then equation of continuity, Bernoulli's theorem, these all points we have discussed. We have already discussed about the excess pressure. So here we can see the excess pressure in different cases. That is, first one we have the plane surface. So on the plane surface, you can see the excess pressure will be 0. That is delta P is equal to it is 0. Okay, then next we have convex surface where this delta P can be written as excess pressure can be written as 2T divided by R. R is the radius of curvature, T is the tension. Then next bubble in air. So for bubble in air, we can see that it is written as delta P is equal to 4T divided by R. It is 4T divided by R here. Okay. Next we have that is concave surface. So for concave surface, the excess pressure is given by 2T divided by R, similar to our convex surface. Then for a drop, it is delta P is equal to 2T divided by R. Again, it is same. Then for bubble in water, bubble in liquid, it is 2T divided by R. So these are the expressions for excess pressure in different cases. Okay. Then next we have angle of contact. So what is angle of contact? Angle of contact between a liquid and a solid. It is defined as the angle enclosed between the tangents to the liquid surface and the solid surface inside the liquid. So both the tangents being drawn at the point of contact of the liquid with the solid. So more than definition, if you see the figure here, you may understand the definition in better way. That is, see here, it is the angle between the liquid and the solid surface. You can see in the given picture. Correct. So here the angle of contact, it will be less than 90 degree for a concave meniscus. It will be equal to 90 degree for a plane meniscus, and it will be greater than 90 degree for a convex meniscus. Okay. So in the first case, liquid wets the solid surface when it is a concave meniscus and when it wets the surface. So here the expression is given by FA is greater than FC by root 2. Then similarly for plane meniscus, when it will not wet the surface, we can see the expression here. Next, here the value of angle of contact, it lies between 0 and 180 degree. Okay, so theta is equal to 0 degree for a pure water and glass. Theta is equal to 180 degree for a tap water, and theta is equal to 90 degree for water and silver surfaces. So theta is equal to 138 degree for mercury and glass surface. Then it is equal to 160 degree for water and chromium. Okay, so like this we have the value of angle of contact different for different surfaces in contact. It is particular for a given pair of liquid and solid. Thus the angle of contact changes with the pair of solid and liquid. Okay. Next, it does not depend upon the inclination of the solid in the liquid. Okay, on increasing the temperature, angle of contact decreases here. On increasing the angle of increasing the temperature, angle of contact, what happens? It decreases. So for soluble impurities, it increases the angle of contact. Partially soluble impurities decreases the angle of contact. So here we need to remember these all points. Okay. It does not depend on the angle of inclination On increasing the temperature, angle of contact decreases. So soluble impurities increases the angle of contact. So partially soluble impurities decreases the angle of contact here. Then next we have capillarity. So what do you mean by capillarity? See here. If a tube of very narrow bore is dipped in a liquid, it is found that the liquid in the capillary either ascends or descends relative to the surrounding liquid. So when you dip a narrow tube inside a liquid, what happens? The water or the liquid rises up in the tube. This phenomena is called what? Capillarity. This phenomena is called as what? Capillarity here. Then next, this completes all the multiple choice questions based on our topic, mechanical properties of solids and fluids. Let us discuss the multiple choice question based on this chapter. So the first question is, A and B are two wires. The radius of A is twice that of B. So here we have two wires. One is the radius of first wire is twice that of the B. They are stretched by the same load. They are stretched by the same load. Then the stress on B is given by. So here we need to calculate the stress here. We need to calculate the stress when the radius increases by twice than the other one. So what is the stress? Which is having more, which is having less? Let us see that. So we have the formula, stress is equal to force per unit area. Stress is equal to force per unit area. So this is nothing but force divided by area can be written as pi r square. Area can be written as pi r square. Therefore, stress is inversely proportional to r square. Stress is inversely proportional to r square. So if I take the ratio here, that is stress of B divided by stress of A is equal to, this is radius of A, as it is inversely proportional, we will get it as radius of A divided by radius of B whole square. So what they are given, the radius of A is twice that of radius of B. So RB will get cancelled. Its whole square it is, RB will get cancelled. Therefore, we will get it as 2 square. So 2 square is nothing but what? It is 4. It is 4 into stress of A. So we can say that the stress of B is equal to 4 times the stress of A. That is option B is the right option. Here option B is the right option. Okay. Next question. On suspending a weight mg, the length L of elastic wire and area of cross section A, its length becomes double the initial length. The instantaneous stress action on the wire is, see here what they have given. The weight of the object is given as mg, the length is given as L for a given wire, and its area of cross section is A. Okay, when the length becomes double the initial length, so what happens to the stress? So what is the relation between length and stress that we need to understand to answer this question here? Okay. So when the length of wire becomes double, the area of cross section will also, it becomes half, because volume of wire is constant. Here volume of wire is constant, therefore volume can be written as what? Area into length. Then instantaneous stress is equal to, so instantaneous stress is equal to, we have a formula, that is stress is equal to force per unit area. This force is written as mg divided by area. So what I said, that is when the length becomes double, the area reduces to half. Therefore, this area can be written as A divided by 2. Therefore, I can write it as 2 mg divided by A. See here, what they have asked, when the weight is suspended, the length L of elastic wire and the area of cross section of A, its length becomes double. Then the initial length, the instantaneous stress of the wire is given by. So we have instantaneous stress is equal to force per unit area. Substitute force is equal to mg divided by area as A by 2. Then simplify this, we will get it as 2 mg divided by A. 2 mg divided by A, that is option C is the correct option here. Option C is the right option, right? Next, a cube of aluminium of side 0.1 meter is subjected to a shearing force of 100 Newton. So you have a cube of aluminium side 0.1 meter, means its length is given, which is subjected to a shearing force of 100 Newton. The force is given, the length is given, the top face of the cube is displaced through 0.02 centimeter. The top face is displaced through 0.02 centimeter with respect to the bottom face. With respect to what? Bottom face. The shearing strain would be, the shearing strain would be. So we need to calculate the strain here. That is, so as we know that shearing strain is equal to, it is x divided by L. So x is, it is 0.02 divided by L. Length is 0.1. Length is 0.1. So 0.02 divided by 0.1 is nothing but 0.002. 0.002 here. That is option D is the right option. Option D is the right option here. Shearing strain is equal to 0.002. Next, a wire is stretched to double its length. The strain is, so when the wire is stretched to its double its length, then the strain. So what happens? Let us see. Because we know the equation directly, we can substitute what data it is. See here, that is strain is equal to change in length divided by original length. Strain is equal to, it is change in length divided by original length. So change in length is what? It is doubled here. Therefore, we will get it as final length minus initial length divided by original length is how much? It is L. So 2L minus L is L. L divided by L is nothing but it is 1. It is 1. So when a wire is stretched to double its length, the strain becomes 1. The strain becomes 1. That is option B is the right option here. Option B is the right option. Next question. The length of a wire increases by 1% by a load of 2 kg weight. The linear strain produced in the wire will be. So what will be the linear strain produced in the wire when the length is increased by 1% and the load is 2 kg weight? See here. That is strain is equal to, it is change in length divided by original length. It is given by change in length to the original length, which is equal to. So change in length, how much they have given? It is given as 1% of L. It is given as 1% of the length divided by original length is, it is L. So this can be written as L divided by 100 divided by L. So what happens? LL will get cancelled. 1 by 100 is nothing but 0.01. 0.01. So when the length of the wire is increased by 1% by a load of 2 kg weight, so we don't require that load value only. Okay, the linear strain produced in the wire will be, see that is 0.01. 0.01. That is option C is the right option here. Next question. The diameter of a brass rod is 4 millimeter and Young's modulus of brass is 9 into 10 raised to 10 Newton per meter square. The force required to stretch by 0.1% of its length is, see, they have given the diameter, Young's modulus value, and the length is given. Then we need to calculate the force required. So we have Young's modulus Y is equal to force per unit area into delta L divided by L. Change in length divided by original length. We require force. Therefore, force is equal to Y into A into L divided by capital L. Therefore, we can calculate force is equal to, what is the Y value, Young's modulus value? It is 9 into 10 raised to 10 into area is not given. Therefore, we will take it as pi r square. So, pi r square diameter is given. Then the radius will be half of that. It will become 2 into 10 raised to minus 3 whole square into, then here we have length. So, length is how much? It is 0.1%. So 0.1%, how can I write it? It is written as 0.01. 0.001. So this is equal to, simplify this one, we will get it as 360 pi into 360 into pi Newton. The unit of force is Newton here. Therefore, 360 pi Newton. That is option A is the correct option. Option A is the correct option here. Next question. A wire of length L and radius R is rigidly fixed at one end. On stretching the other end of the wire with a force F, the increase in its length is L. If another wire of same material but of length 2L and radius 2R is stretched with a force of 2F, the increase in its length will be, see here what all they have given. A wire of length L and radius R is rigidly fixed at one end. It is fixed at one end. So we are stretching the other end of the wire. The increase in its length is L. Okay. If another wire of the same material of length 2L and radius is 2R is stretched with a force of 2F, then what will be the increase in the length? So same material, different wire we are taking. That time, what is the increase in the length? When the force is doubled and radius is also doubled. So see here, we have the expression L is equal to F into L divided by pi R square into Y. Correct. So it can be written as, I'll take the ratio L2 divided by L1 is equal to, it becomes F2 divided by F1 into L2 divided by L1. So pi and radius, this one Young's modulus will get cancelled as they are same, into R2, sorry, R1 divided by R2 whole square. this is equal to. So what they have said, the force is doubled. Therefore, it becomes 2F divided by F. That is nothing but F will get cancelled. We will get it as only 2. The length is also doubled. Therefore, here also we will get it as only 2 into. So this is 1 divided by 2, its whole square. So 2 will get cancelled. We will get only 2 by 2 again. 2 by 2 again, it is nothing but 1 here. 2 by 2 again, it is nothing but 1. Therefore, here we got it as L2 divided by L1 is equal to 1. So what we can write here, students? We can write it as L2 is equal to L1. So the increase in the length will be same as that of the initial, even though force, radius and length initially if it is doubled. Okay. So option A is the right option. Option A is the right option here. Next question. Two wires A and B are of same materials. Two wires A and B are of same materials. Their lengths are in the ratio of 1:2 and diameter are in the ratio of 2:1. When stretched by a force FA and FB respectively, they get equal increase in their lengths. Then the ratio of FA by FB should be. So you have two wires A and B of same material. Their lengths are in the ratio of 1:2 and diameter is in the ratio of 2:1. So when it is stretched by a force of FA and FB respectively, they get equal increase in their length. Then the force ratio FA by FB should be. That is. So we have a formula. Y is equal to, that is Young's modulus is equal to F into L divided by pi r square into small l, pi r square into small l. So simplify this equation for F is equal to, this becomes F is equal to Y pi r square into L divided by capital L. What we need to do now? So this is the general equation. For A and B, take the ratio. It becomes FA divided by FB is equal to, FA divided by FB is equal to, it becomes YA divided by YB into pi r square. Pi will get cancelled. So r square, it is written as RA divided by RB, its whole square, and LA divided by LB into, this is LB divided by LA. So this is equal to, so this value is 1 into 2 divided by 1 whole square into, it is 1, then next into 2 divided by 1. So 2 square is 4. 4 into 2, it is 8. It is 8. So we will get it as 8 divided by 1. That is nothing but 8:1. 8:1. So if you see, the option D is the correct option here. Option D is the right option. Then the next question is, option D is correct option here. Let us see the next question. The Young's modulus of wire of length L and radius R is. So the Young's modulus value is given for the length of wire R, L, and radius is R is Y Newton per meter square. If the length and the radius are reduced to L by 2 and radius is by half, then its Young's modulus will be. See here what happens. Young's modulus, it do not depend upon the dimensions of the wire. It is constant for a material of the wire. The Young's modulus, it depends on the material. It does not depend on the dimension. Whatever may be the dimension, if it reduces, increases, whatever it is irrespective of the dimensions. It depends only on the nature of the material. Okay. So that is, if Y is the Young's modulus for a given length and radius, if it is doubled also, the Young's modulus value will be same. Therefore, option B is the right option here. Then the next question. A wire suspended vertically from one of its ends is stretched by attaching a weight of 200 Newton to the lower end. The weight stretches the wire by 1 millimeter. Then the elastic energy stored in the wire is. So what is the elastic energy stored in the wire? They have given the weight and length. Energy stored we need to calculate. So already in the synopsis we have discussed energy stored U is equal to, it is 1 divided by 2 F into L, that is equal to 1 divided by 2. So force is how much it is? 200 Newton into length is 1 millimeter, that is 1 into 10 raised to minus 3 meter, which is equal to, so 2 ones are 2100. 100 by 1000, it is 0.1. So it is 0.1 joules. It is 0.1 joules. That is option A is the correct option. Next question. When a 4 kg mass is hung vertically on a light spring that obeys Hooke's law, the spring stretches by 2 centimeter. The work required to be done by an external agent in the stretching this spring by 5 centimeters will be. So they have given a mass as 4 kg. It obeys Hooke's law. The spring stretches by 2 centimeter. The work done on the spring is, when it is increasing by again 5 centimeter. So acceleration due to gravity is given as 9.8 meter per second square. The expression, when a 4 kg of mass is hung vertically on a spring, it stretches by 2 centimeter. So here the force constant is denoted by K. That force constant K is equal to, we have formula F divided by X. So how much is the force here? Force is M into G. Mass is 4 into G is acceleration due to gravity is 9.8 divided by X is 2 into 10 raised to minus 2. So this is equal to, if you simplify this, we will get it as 1960 Newton per meter. 1960 Newton per meter. So what is the work done in stretching the spring by 5 centimeter? So the potential energy is equal to 1 by 2 K into X square. That is equal to 1 by 2 into K. How much we got? It is 1960 into X. It is already given as, again we are increasing it by 5 centimeter. So it is 5 into 10 raised to minus 2 X square is whole square. This is equal to, so simplify this, we will get it as 2.45 joules. 2.45 joules. That is option A is the right option. So we need to calculate the energy, and that is given by half kx square. So to calculate energy, we require K, force constant. force constant is given by F divided by X. Okay, so option A is the right option here. Next. A wire of diameter 1 millimeter breaks under a tension of 1000 Newton. Another wire of same material as that of first one, but of diameter 2 millimeter, breaks under a tension of. So here we need to calculate the tension is nothing but there is force acting. They have given when the diameter is 1 millimeter, the tension is given as 1000 Newton. When the diameter becomes 2 millimeter, what is the force? Here we know that is braking force is proportional to area of cross section. Braking force is directly proportional to area of cross section, and that is pi r square.